All right, so as I was saying, the constellations change position over the course of over the course of time. Of course, that is just us. I mean, all right, let me back up just a little bit. So over the course of a night, the constellations are moving from east to west. Of course, that's because of the rotation of the Earth, right, about our own axis, the spinning, once every 24 hours. But if you go out and you look at the constellations, right after sunset, let's say in the western sky, um, the, these constellations will move to the west over the course of months, and then you won't be able to see them anymore because, of course, they're in the same direction as the sun is. So you can actually see this much better here. This is a good description of it. So as our year takes place, the here's so of course the Earth is tilted by 23.5 degrees, and that tilt, by the way, remains the same it remains in the same direction, no matter what time of year it is. All right, so let's talk about the different constellations. So let's say in December, you look out and let's say Gemini is directly overhead. In 3 months later, let's say in March, you look and Virgo is directly overhead. 3 months later, then Sagittarius is directly overhead. 3 months again, let's say, well, not direct. I shouldn't say directly overhead. Sorry, that's actually not a good description. All these constellations. These are the constellations of the zodiac. They all are a line called the ecliptic passes through these, and so the sun moves through these constellations with respect to us. As the year progresses, and so I guess I should mention this really quickly. So traditionally there's 12 constellations of the zodiac. There's actually a constellation between Scorpio and Sagittarius called Ophiuchus that's never mentioned at all in when people talk about zodiac, signs of the zodiac and so forth. But there is a little part of the sun's path brings it through the constellation Ophiuchus. It's not really shown here, but that does happen. All right, let's talk about angular measurements because we use this all the time when we talk about objects in the sky. So, for example, there's the Big Dipper. These two stars right here are called the pointer stars. Just to let you know, if you look at the Dipper in this manner, where here's the handle. These two stars point in the direction of the North Star. That's why the Big Dipper is often used that way. So angular measurements are, of course, in what are called degrees, where one complete circle is 160 degrees. But then we break a single degree into units, into fractions, and what is generally used in astronomy is called arc minutes. So in 1 degree there's 60 arc minutes, and then in 1 arc minute you're talking about a much narrower region of sky. There are 60 what are called arc seconds. Now, with the human eye, we can see objects down to about 1 arc minute, but we can't without binoculars or a telescope. And of course, the more powerful the telescope, the more fine of detail that you can see. But with just the naked eye, you can only see down to about 1 arc minute. Just to give you an idea, as a reference, for example, the full moon is about 30 arc minutes across. All right, so again, arc seconds are taking one arc minute and breaking it into 60 equal chunks. And there's actually a really good. This is an excellent PowerPoint slide that shows you that. So here's 1 degree broken up into 60 arc minutes, and then 1 arc minute is broken further into 60 arc seconds. So, the most powerful telescopes on the planet can see down to even a fraction of an arc second, very small fractions of arc seconds. But that's, the largest telescopes on the planet. All right, so let's see. So if your finger was one degree, let's say you held your finger at arm's length, and that's roughly 1 degree. How many arc seconds would that be? All right, and so it's actually, the answer is 3,600 arc seconds, because there's 60 arc minutes in 1 degree, and then 60 arc seconds. So 60 times 60 gives you 3,600 arc seconds. All right, so this is used all the time. In this class, we're not really going to use too much math, but we just kind of talk about it. We don't actually do a lot of equations in this particular math, or in this particular class. So there's what's called the diurnal motion, which is the daily motion of objects in the sky. It's really, the motion of us, rotating around, and so there's actually because the Earth is actually, as you know, moving around the sun. One 24-hour period, the Earth has moved a little bit. It has shifted. So in astronomy, we often talk about what's called a sidereal time, or a sidereal day. And so the sidereal day shifts, from our perspective, a little bit each day, because of course the Earth is going around the sun, and it's actually very useful when you talk about where a particular star is. You usually refer to the sidereal time. Anyhow, there's conversions and stuff. We don't have to worry about that, but just to let you know, there is this thing called sidereal time, which is really based on the stars. The stars, we talk about the stars being fixed, because they're so far away. Any actual movement of a particular star, we'll never ever see. And even in thousands upon thousands of years, you're never going to see a star move across the sky. The stars that we see are pretty much the exact same patterns that the Greeks and other people saw. All right, so the motion of the Earth, of course, all the planets are along a plane, a flat plane, or relatively flat plane, that matches up with the ecliptic, which is, of course, the path of the sun. And the Earth is actually tilted, as I mentioned earlier, 23.5 degrees with respect to the ecliptic, and really that's why there are seasons. So I mentioned this before. This tilt remains constant throughout the year, and it actually remains constant over millions upon millions upon millions of years. Anyhow, so really the tilt is what causes the seasons. All right. So for example, let's say in the northern hemisphere, let's just concentrate on the northern hemisphere. The southern hemisphere, of course, is doing the opposite. So during the summer solstice, which, for the northern hemisphere, that happens right around June 21st. It's not always June 21st, but usually it's, either a day before or a day after, so sometime around that. anyhow, what's happening then is because of the Earth's tilt, that is a time during our year that the northern hemisphere is tilted towards towards the sun, more directly towards the sun. So imagine like rays of sunlight. They don't get as spread out across the northern hemisphere as they would 6 months later, right? 6 months later, the Earth is tilted away, or the northern hemisphere, I should say, is tilted away from the sun. And so what happens is those same beams of sunlight are spread out over more area. And actually, that's why it's colder in the winter and warmer in the summer. It's really the angle that the sunlight hits our Earth. All right, and of course, there's two times where there's an equal amount of day and night, and those are called the vernal or the spring equinox, and then the autumnal or the fall equinox. All right, and they of course occur on March 21st for the vernal, and roughly September 21st for the autumnal equinox. Now, I did mention to you that, of course, the Earth's tilt stays relatively constant. That's not exactly true. It turns out, and just a quick explanation for this, the Earth, because it's spinning, it's actually because the Earth and the Moon system, the Earth's spin is actually slowing down. It's slowing down very, very slowly, but what happens is because the Earth is slowing down, it wobbles a little bit, and we have a technical name for that wobble. It's called precession, and it's extremely slow. So this is, it's like a top slowing down. If you spun a top, you would watch it, start to wobble, and the Earth is doing that too. However, the wobble, this thing called precession, takes 26,000 years to wobble around once. All right, so it's extremely small. Nobody's ever going to see that in their lifetimes. It's a very minor thing, but it's something that we've actually been able to measure, and yeah. So, all right. There's the thing about the fixed stars. All right. So, all right. Again, latitude and longitude are, of course, on the Earth. We use right ascension and declination for the celestial sphere, for objects in the sky. Let's see, do they talk about that here? Yeah, all right. This is, if you're at 50 degrees, then if the North Star is at 50 degrees, then you're at 50 degrees. So that C is the right answer there. Let's see. Why do we see phases of the moon? Okay, so it's actually the changing angle between the Earth, the moon, and the sun. So the moon is always half of the moon is illuminated, but we don't see it that way because, of course, the moon is going around us. The moon is going around the Earth. So we see various what are called phases, and the phases take a little more than 27. Actually, the phases take about 29 days to go through all the phases and then repeat. And here are the phases. So there's new moon, and then waxing just means that the crescent. The waxing just means that the crescent is getting greater and greater. So this is a crescent moon. Down here is a crescent moon, and then the crescent gets greater and greater, and then you get a point where the Earth and the moon and the sun are at 90 degrees with respect to each other, and that's called first quarter. Now let me